Hello, everyone, and welcome to our live stream. This is, we are coming live to you from Steward Observatory in Tucson, Arizona. We're all back together again. It's very exciting. My name is Matthew. I am one of the course staff and instructors for our online classes, but we know that people will join us from all over the place, and we are glad to have you here. I'm going to hand this over to Professor Impey, who's going to welcome you, and then we'll get started with your questions. Please post those questions in the live chat, and we will grab them from there. We're trying a slightly new setup today with slightly new audio since we're both in the same location. So if things are a little strange, then bear with us while we get used to our new old setup again. So Chris, go ahead.
Okay, thank you, and welcome everyone to another live session for the online courses, or whoever happens to stop by. So happy to take your questions about pretty much anything in astronomy.
Excellent. The first question is from Parth, who asks, what happens to the atoms that make up the singularity? Are they even atoms, or are they just quarks, or the gluon field, or strings? But what happens to subatomic particles and atoms when they go into a singularity?
That's a good question, but actually we don't know is the simple answer, and the slightly longer answer is, since a singularity is essentially a mathematical entity, it's an infinity of space density, of rather mass density, that's a non-physical situation. So almost by definition we don't have a physical theory to describe what happens to matter at a singularity, because particles have an extent, they have mass, and so a singularity represents a sort of an unphysical situation. And unfortunately, that's all we can really say about it.
Excellent. Thank you very much. The next question is, again, from one of our live viewers who asks, do you think that, this is from Demetrius, who asks, do you think that there is any chance that the International Astronomical Union will accept public voting or other alternatives for naming celestial objects, especially potentially habitable exoplanets?
It's a good question, and I think the answer probably is no. The International Astronomical Union, of which I'm a member, and they have about 10,000 members worldwide, it's a pretty conservative body. And in the past, when early exoplanets or even extraplanets in the solar system were found, and the astronomers who discovered them attempted to name them, those names were essentially overruled. And the IAU has shown really no signs of deviating from its method of assigning names based on mythology, or now they've sort of opened it up from the sort of Western-centric Greek and Roman realm of gods and goddesses to other cultures and civilizations around the world. So they're at least getting a little more open-minded about that. But they don't tend to go in the direction of public voting for names of things. It hasn't ever happened in the past, and I really actually don't see that changing, unfortunately. So you're going to have pretty stodgy names for astronomical objects for the foreseeable future.
Excellent. Thank you very much. The next question is, again, from one of our live participants. World of Science asks, what is the best way to consider gravity? A force or a curvature in space-time, a field created due to mass, or something else?
The force concept really revolved around Newtonian gravity. That was a concept that dates back to Newton and even earlier. And the problem with the force concept is always, what is the carrier of the force? I mean, gravity operates across a vacuum, essentially across an infinite distance in space and time. And so it's never very clear in physics terms what is the carrier of the force. So you hypothesize in modern particle physics a graviton, a particle which has never actually been observed. So I think the force concept has sort of become outmoded in modern physics. General relativity, of course, replaces that with the idea of curved space-time, and particles or light traveling the shortest distances in curved space-time, which are called geodesics in general relativity. And that becomes a different way of thinking about gravity, because the particles are on ballistic trajectories, but not in a linear space-time, but in a curved space-time. And I think that is the most sensible way to think of gravity. You can also think of gravity as a field, and fields are a common part of modern physics. That's how we understand a lot of subatomic physics too. And so I think a field is a reasonable description. It's a reasonable description for calculating force and the effect of gravity. But the true underlying description is in terms of curved space-time.
Excellent. Thank you very much. The next question is from Art Studio, who asks, what is responsible for the spikes or the hills in the electromagnetic field of the Bose-Einstein condensate? We'll end there.
Right. The Bose-Einstein condensate is a state of matter. The naming of it, Bose and Einstein, was after a famous Indian physicist and contemporary of Einstein who developed the behaviors of particles that have integer spin. Those are bosons. Particles like electrons, for example, that have half-integer spin are called fermions. So there are two fundamentally different types of particles in terms of their spin, their quantum spin. We shouldn't really think of them as spinning tops. So Bose-Einstein condensate is a coherent state of matter that occurs at very low temperatures. It was created in the lab. It led to the award of several Nobel Prizes, actually, some 20-odd years ago. And once you see this kind of coherent behavior of matter at very low temperatures across significant distances, that also plays into how electromagnetic waves interact with that matter. And that's what gives these interesting patterns that the question is alluding to in the radiation associated with the Bose-Einstein condensate. So it's a very esoteric form of matter. It does have potential implications for superconductivity, for advanced forms of electronics, but at the moment it's more of a curiosity of a physics lab.
So that really does go to the next question, which is there any chance that we might find this in nature? So maybe you can just specifically address that.
It's very unlikely that any natural astrophysical setting would create a Bose-Einstein condensate. There are certainly parts of the universe that are cold enough for that situation, but there are not. But it's also a situation where you have to contrive matter into a particular configuration. So it's not a low density situation. Most of the cold situations in the universe are very low density. So there's no natural situation we know of where the density is high and the temperature is very low, which is essentially what you need.
The next question is from one of our live participants, Alec. And Alec asks, do you think that humans are parasites to the Earth, or are humans parasites to the Earth, or could they be considered parasites on Earth?
Well, it's an unflattering description of humanity, but in some degree, I suppose it does fit. We are the alpha species, if you like. We're the top of the food chain on the Earth, and we have sort of used our position and our intelligence and our technology to damage the planet substantially. So while we may not formally fit the definition of a parasite, that's a description that has a particular meaning in the animal kingdom or in the world of biology. We certainly are parasitic in the sense that we're living off the planet in sort of unsustainable ways, the prime example, of course, of which is the dependence on fossil fuels. And we've just had a very stark reminder in the 6th report of the IPCC of just how close we are to a problem there. The other problem that goes along with that is our use of resources. If you project land use and degradation of natural environments into the future, you come to a time only about 20 or 30 years from now when all usable land will be used by us for various purposes, agriculture, building cities, and so on. At that point, there's no extra land. There's no land to have for planting crops. There's no land to live on beyond what we already use. So that's an unsustainable trajectory. And in that sense, yes, maybe we are parasitic.
Excellent. Thank you very much. The next question is, can you talk about meteor showers? There are a few people who are asking, what is a meteor shower? When is the next one? Can you talk a little bit about what they are, where they come from, and when we might see some?
Sure. Meteor showers in general are situations where the Earth passes through the debris trail of a periodic comet. So there are many periodic comets, of course. All comets that are in bound orbits of the solar system have a period. But these are typically short-term comets that have periods of months up to years to decades. And while you think of the material being attached to the comet, actually material is coming off the comet all the time, and sometimes large chunks are breaking off. So in its periodic orbit, debris gradually gets stretched around the entire orbit of the comet. And so it's not just a question of where the comet is in the sky, it's where the Earth is relative to the orbit of the comet, which is filled with debris. And so in the situation of a comet whose trajectory crosses the Earth's orbit, the Earth will cross the debris trail of that comet. So it's not like the comet might hit us, but at any time in its orbit, we may be passing through some of the debris. And since that's a periodic phenomenon, it'll repeat year after year as the Earth moves in its orbit of the Sun. So all the main meteor showers correspond to our intersection in our orbit with a comet orbit and the debris in that. And so the things we see in the night sky are the small particles, typically, from boulder size down to pebble size, and mostly actually grains of sand sized particles that come into the upper atmosphere and burn up. Almost none of them reach the ground. And that's the meteor shower. And the naming of the meteor showers really relates to the constellation they're seen in, which tells you essentially what time of year they occur. The Leonids, obviously, in the constellation Leo, the Perseids in the constellation Perseus, and they recur from year to year. And the reason the meteor showers vary so dramatically from year to year, and the reason why they're unpredictable in terms of how many meteors you might go out and see, is because the debris strewn along a comet path is highly non-uniform. So some years we may go through a pretty dense patch of debris, and you'll get a huge meteor shower with maybe 10 to 30 events per minute. And other times you go through a very sparse patch and the meteor shower is a bit of a bust, and it's very hard to predict.
Excellent. Thank you very much. The next question is from, again, one of our live participants who would like to know, Ilsa Martin asks, there are several terms for outer space, like the Kármán line at 100 kilometers. Is the word interstellar at a specific distance too, or how real are these terms for things in space?
Yeah, that's a good question. There's been a lot of debate about the boundary to space. Because as we saw recently with these billionaires going into space, Richard Branson did not reach as high an altitude as Jeff Bezos did. And Jeff Bezos got to the Kármán line, which is essentially 100 kilometers. And that's the formal definition of space that almost everyone would agree on. Richard Branson didn't get to the Kármán line. The reason for that is interesting. His rocket, Spaceship Two, actually had to be de-scoped because he couldn't get enough power out of the engines without the engines becoming unstable or there being problems. So he had to scale back the power of his rocket, and that stopped him from being able to reach the Kármán line. So he reached a lower altitude, which NASA chooses to declare as space, but is not internationally recognized. And we should recognize that both of the altitudes reached by Branson and Bezos are well below what most people think of as space, which is low Earth orbit. And neither of these people went into orbit. And Earth orbit is more like 200 miles up, 200 to 250, and high. And some satellites are in high Earth orbit at 350 kilometers. So it's a movable target. But the Kármán line is the most generally accepted definition. But it's obviously a round number. The atmosphere thins out continuously as you go up, so it's at some level an arbitrary round number. As for the edge of the solar system, there are similar difficulties in definition, because you could choose it to be the outermost orbit of the planet, and the outermost planet being Neptune. We've demoted Pluto, so we don't use it as the outer bound. But that's not right, because there are a lot of objects in bound orbits of the Sun in the Kuiper Belt. And the Kuiper Belt extends from 40 to 80 astronomical units. So you could say the solar system ends at the Kuiper Belt. But there's still rocky material out there, just it's less dense. So what astronomers tend to use as the outer bound of the solar system is what's called the heliopause, and that's the distance at which the solar wind runs into the interstellar medium. And so you really do transition to a different physical state of the very low density medium that a spacecraft is traveling through. And we have, of course, had 4 spacecraft, the Voyagers and the Pioneers, launched in the 1970s that have now reached the heliopause, that have now reached the interstellar medium. By common ascent, they have moved beyond the realm of the Sun into the realm between stars.
Excellent. The next question is from Everything Psi, who would like to know, does sound travel faster in space?
Sound doesn't travel in space because sound is a compression wave of atoms or molecules. So sound on the Earth represents compression waves caused by the motion of air. When you talk or when a musical instrument plays, it's pushing air in cyclic manner, and that cyclic compression and rarefaction leads to pressure waves through the medium. And the pressure waves are essentially the molecules or atoms just pushing against each other in sequence, moving outward. In the realm of space, there are essentially no atoms. So it's not a complete vacuum, but it's very close to a vacuum. So there's no way for sound to be carried the way it is on Earth. So essentially, you need an atmosphere to have sound. It doesn't have to be the Earth. It could be any atmosphere. So Mars has a very thin atmosphere, but technically, sound could be carried in the Martian atmosphere. But when there's no atmosphere, there's no sound.
All right, the next question is from one of our live participants. Art Studio would like to know, how does spectroscopy help in the study of astronomy and the images of the universe that we have?
So spectroscopy is a very critical tool of astronomy. The whole subject has been immeasurably improved by spectroscopy. We haven't always had spectroscopy. We've had imaging of astronomical objects since the telescope was invented in 1600 or just after, and it took another 200 years for spectroscopy to be developed as a tool. It was Joseph Fraunhofer, a brilliant young scientist who died unfortunately young in Germany, who developed what is the commonly acceptable method of dispersing light into its constituent colors and then using the way the intensity of light varies with wavelength to diagnose spectral elements. And essentially, spectroscopy is how we know what the universe is made of. We didn't know what stars were made of. We didn't know what galaxies or the universe itself was made of until spectroscopy. Spectroscopy matured through the 19th century and was obviously importantly allied with developments in photography, so you could capture a spectrum in a photographic emulsion. In the modern realm, spectroscopy is still used by astronomers all the time for similar things, and you can do spectroscopy at other wavelengths too. We have instruments on the Hubble Space Telescope that do infrared spectroscopy. The Chandra Observatory does spectroscopy at X-ray wavelengths, and there are plenty of radio telescopes that disperse radio waves into spectra. So you can do spectroscopy with any type of electromagnetic radiation, and they all are telling us important things about the universe.
Excellent. The next question is related, and it's about the dark lines that are caused in a spectrum. So can you talk about what those dark lines are? This person who asked the question says the dark lines which are caused by obstructions of the light by an object. Is there any way to fix these obstructions? Maybe we can sort of set them straight on what those dark lines are.
Right. So in a spectrum where you see dark lines, those are called absorption lines in the terminology. And the classic example we would use is the spectrum of the sun, because that was used, the first spectrum of the sun was made 200 years ago, showing that these dark lines crossed the sun's spectrum. And these lines corresponded to the wavelengths of transitions, atomic transitions, in the most abundant elements in the sun. Not just helium and hydrogen, but sodium, calcium, and so on. These are trace elements in the sun, but they imprint their presence by absorption lines. So why are the lines dark or black? Why is the light taken away at that point? It's because as you move outwards in the sun or any star, the material gets cooler. And so the source of the light, the photons, is the interior of the sun, and the light is traveling outwards. Well, when it meets cooler material, then those atoms interact with that light, and they absorb the light corresponding to the wavelengths of their atomic transitions, electrons moving up and down in their energy levels. So as light comes outward and hits these elements, hydrogen, helium, calcium, sodium, whatever it is, the light is absorbed at those particular wavelengths corresponding to particular energies of electron transitions in the atom, and it's absorbed coming outward from the sun. But when the atom re-radiates that radiation, as it will do, it re-radiates it in every direction. And so because the source of the radiation is coming from the sun and going radially outward, but the atoms that absorb it in the cooler outer layers are radiating that same photon, or that same set of photons in all directions, we see a net deficit of those wavelengths of photons coming on towards us and reaching the telescope. And that's why you see notches or dark lines in a spectrum to represent absorption. So it is indicating there's a cooler material beyond the place where the photons were originally created.
We do have a couple of moon-related questions. Sunil sent an email and asks, will there be any chance of crashing our moon onto the Earth?
No, it's going the other way, actually. Because the tidal interaction of the moon with the Earth, the moon is tidally locked to the Earth, which is why we see the same face all the time. There's a gradual transfer of angular momentum and energy between the Earth and the moon, because they're interacting gravitationally quite strongly. And the nature of that interaction is that the moon is getting about 1 centimeter further away from the Earth every year. Tiny amount. It's been measured because we have reflectors on the moon and have measured highly accurately the distance to the moon. So the moon is gradually moving outwards, and that transfer of energy and angular momentum is also causing the Earth to spin down slightly in its spin rate. So the day is getting very slightly longer every year as well, by about less than a millionth of a second, I think. So no, there's no danger of the moon crashing into the Earth, and if anything, it's going the other way. Eventually it'll escape from the Earth, but a very long time in the future.
So our next moon-related question is related to a news story that has been out. Can you explain the news story that the moon's wobble will somehow affect the tides and will make the effects of climate change worse in the 2030s?
So the moon does have the moon obviously is the cause of the tides, and because the moon is exerting a stretching force on the Earth, because the moon is a pretty large satellite of the Earth, and so it pulls on the near side of the Earth stronger than it pulls on the far side of the Earth, and it pulls on the ocean on the near side to the moon slightly stronger than the ocean on the far side, and that amounts to a stretching force. So the entire Earth is being stretched by this, but it's solid rock. The water, however, can flow, and so that means the moon is tugging the ocean that's close to it towards it, and on the far side, the ocean is moving away from it. And as the Earth rotates, that corresponds to 2 tides a day. Now, if that were all that was going on, nothing would change. But the Earth-Moon system is doing other things. The Earth-Moon distance changes on a particular cycle, and the Earth has a wobble, or a sort of oscillation of its tilt axis, and that has a more like 18-year time scale. And since it is the orientation and distance of the moon that causes the tides, anything else added to the Earth-Moon system that away from a simple circular orbit will also enhance or decrease the effect. So there's this extra cycle imposed on the tides, and we're approaching a period, the 2030s, where the moon effect on the Earth and the tides will increase somewhat. But it's not a dramatic effect. It's not like the tides are going to double. It's going to be a marginal effect. However, we're in a situation now with climate change and the oceans rising around the world where even a small effect, even a few centimeters on a tide, or certainly a foot or so on a tide, on a high tide, could have a dramatic influence. And so it seems that this period of time will make things worse as far as tidal surges go.
Thank you. The next question is from Jennifer, who is on with us live, and asks, how many planets are in the Milky Way galaxy? And she's pointing out that she just wants an estimate.
Sure. The best guess now, based on Kepler and all the exoplanet work so far, is there's at least 1 planet per star in the Milky Way galaxy. That's the simplest way to think of it. And that's all kinds of stars, not just stars like the sun. And in fact, most stars in the galaxy are dwarf stars, red dwarfs, and so most of the planets will be around red dwarfs. So basically, you just have to say, what is the number of stars in the galaxy? That's actually not a very well-determined number because it's hard to measure and count the number of faint red dwarfs. But it's somewhere between 300 and 400 billion. So that's essentially the minimum number of planets in the Milky Way. It could be significantly more, though, because we have not found all the small planets the size of Mercury or even Mars in large numbers.
All right, the next question is from Mayful, who asks, do you have any advice about solar filters that are made at home, or we can talk more generally about what are some good solar filters that people might be able to use to observe the sun?
Right. So if you're doing an amateur astronomy situation, obviously eye safety is the primary concern. So never make any direct observation of the sun. That's the first thing that has to be said always. So always use indirect imaging methods. In other words, if you're observing either binoculars, even more so, because you're supposed to put your eye behind them, and that won't work at all. So, but with a telescope, you can re-image the sun onto a sheet of card, or into a light box where you can see a good image. The solar filters that are out there serve a number of purposes. They often are used to highlight particular features of the sun. So the most common narrowband filter used is H-alpha. H-alpha is a hydrogen line where strong hydrogen emission shows. And so when you use an H-alpha filter, you essentially shut out most of the light that would be coming through and enhance or only leave behind the light from excited hydrogen. And so that's a very good way to visualize or see the prominences of the sun and its halo, or its part of its corona. So the H-alpha is the prominent one, but there are other filters people have used. And often you're just using a neutral density filter, which is essentially a way of cutting down the illumination of the sun by a fixed but large amount, like a factor of 10 or 50 or 100.
The next question is from one of our live participants. Parth asks, what is the use of constellations in modern astronomy?
They have no use in modern astronomy. They have a lot of historical significance, so astronomers are loath to give them up. But astronomers, of course, don't think about stars in terms of constellations in their work. Astronomers who study bright stars, remember the bright stars, the constellations are made up of stars visible to the naked eye, which means they're all brighter than about 6th magnitude. So those are pretty bright stars. Those stars all have names. They're all in astronomical catalogs and have names. And some of them, of course, have Roman, Greek, or Arabic names, and others have numbers from catalogs they're in. So that's really how astronomers think of the stars and the constellations, rather than what constellation they're in. However, the naming of stars often embeds the constellation they're in. And so, for instance, Rho Ophiuchi would be an example of a star, which is in the Ophiuchus constellation, and it's the sequential number in the Greek alphabet that's the letter Rho. So these naming conventions often use the constellation as part of the star name. So that's the way they sort of retain their relevance to modern astronomy.
Bob Denton asks, are Mars rocks less dense than expected, or are they just targeting the wrong rocks?
Well, Mars rocks I'm not sure. The question may be relating to the rover and its difficulty in drilling. There's a general question here too. We have about 100 or more Mars rocks in our possession because they're Martian meteorites, and those Mars rocks are quite dense. In fact, they tend to be igneous. They're volcanic rocks. It's essentially bad luck that no Martian meteorites have come to us that are sedimentary rocks. Now they would be more fragile. Maybe they wouldn't survive the trip, but they would be the ones where we might see evidence of life. So that's unfortunate, because igneous rocks have had a tortured history of compression and extreme heat, and you would not expect life traces in them. So there are plenty of dense Mars rocks because it's a volcanic planet, and there are less dense rocks, sedimentary rocks, as we have on the Earth. And in fact, overall, the range of Martian geology is no different from the range of terrestrial geology. The current rover, Perseverance, has been having problems drilling into the Mars regolith or soil, trying to get, for example, first samples that it can then cache for a later sample return mission. It's teething problems of the mission. I'm sure they'll be able to find slightly softer rocks, because there is a good variety of rocks where the rover is doing its work.
The next question is from Dave Hayden, who asks, what kind of alerts, I'm not sure what they mean by alerts, but just information, what kind of information will the LSST, the Vera Rubin Observatory, produce for the public, such as supernova, nova, GRBs, or new asteroids in need of position data? Oh, I see. So what kinds of information will they post that's like timely and may need input from the public?
Right. The LSST is committed to making its data public. That's a formidable undertaking that they haven't completely figured out how they're going to do, because it's roughly 20 terabytes of data it takes every night, and they're committed to not just, that's the raw imaging itself, to make useful data for the public. They have to filter that data to find the astronomical objects, attach brightnesses to them, compare them to a database, and of course measure things that have changed in brightness, because that's what it's doing. It's doing what people have called celestial cinematography. And yes, alongside with the data dump, which would be overwhelming for any civilian, anyone without a supercomputer to help them, they are trying to make it simpler by letting civilians, citizen scientists, or just the members of the public set alerts on their smartphones, probably, so that they can be alerted when LSST finds a new set of supernovae, for example, or finds a new variable object of any kind, or a star that unexpectedly brightened. And so yes, there are a series of alerts planned. Many of these will go to professional astronomers, and many of them will be objects so faint that nobody could really do anything with them unless you had a large telescope. But it would be interesting to be able to set up an alert to see a quasar, a distant object 10 billion light years away that had flared overnight, and download that particular data and that light curve onto your phone. That would be pretty cool. That's the kind of thing they're committed to. Or to see which supernovae had gone off in the last week, and to download that to your phone or your computer to stare at over breakfast. That's essentially what they're hoping to do.
That is going to be really spectacular. King, who's on live with us, asks, why do stars twinkle?
Stars twinkle because the Earth has an atmosphere. As seen by the Hubble Space Telescope, stars do not twinkle at all. They just are absolutely steady in intensity and absolutely sharp points of light. But as starlight reaches the edge of the Earth's atmosphere, where the waves of light are traveling in plane parallel waves, the varying density of the Earth's atmosphere, both as you go down to the denser regions, but also variations in density due to convection in the atmosphere itself, those cause slight deviations in the direction of the light traveling. And that's because the speed of light depends on the density of the medium it's traveling in. So it's really the temperature and density variations of the turbulent Earth atmosphere that cause slight deviations in the direction of light rays passing through the atmosphere. And the net effect of all those deviations is to jumble the light up for a star or any object, and that's what leaves it twinkling. The jumbling is twinkling because this is varying all the time. The atmosphere is in motion, and so these deviations that pertain to a particular ray of light will change over time, and that's why it looks like a twinkling effect.
The next question is from Parth, who asks, are there any updates on the James Webb Space Telescope?
No, it's still slated to go in October. It doesn't have a strict launch window. Mars missions, for example, it's well known, have sort of 18-month launch windows, and then they have to wait to the next one for the most efficient way to get there. The James Webb is going so far from the Earth to Lagrange point that it doesn't really matter when it's launched, as long as the launch vehicle is available. Now that can be a limitation too, because James Webb is a large telescope and there is only one launch vehicle that can take it up, but it's a pretty flexible launch window. So far there's no sign that they're going to slip that date. There's very strong pressure not to, because the cost overruns of that project, approaching $10 billion total price tag, are already formidable, and Congress has shown some impatience with the project over the years. So I think it's pretty much going to go as planned.
Excellent. So a follow-up to that is, what is, in your opinion, the most relevant discovery that could come from the James Webb Telescope?
Well, the thing that it was touted for, not beyond anything else, because James Webb will do work on exoplanets and other things as well, was what's called first light, and that is the time in the universe when the first stars and galaxies formed. With Hubble Space Telescope, as good as it is, we have seen back not to the dawn of time, but to within about 500 million years of the Big Bang. So that's pretty far back. The universe is 13.8 billion years old, so it's seen back over 13 billion light years away, and to within 5 or 7% of the age of the universe from the Big Bang. James Webb will have to do better because already there were galaxies and stars in place. And we don't know which came first, galaxies or stars, so that's a big question James Webb will answer. The reason it can do so is because it's working in the near infrared. The further light travels through the universe, the more it's redshifted. And the further away it is and the further back in time it is, the higher the redshift. And that means the light that started out in visible wavelengths has been stretched by the expansion of the universe into the infrared. And so James Webb can only look for first light because it works at infrared wavelengths.
The next question is from Hernan, who asks, in the sci-fi movie Europa Report, the Voyagers take some 10 years or so to get there. Could humans really survive the cosmic radiation that they would receive with this, extended mission that they, take to save fuel? Is that even reasonable?
They could survive, but the risk would be very high. On the normal trajectory of a mission to Mars, the estimate is that a human will get, in the 8 months, say, travel time, the equivalent of a lifetime's worth of radiation dose from cosmic rays and solar radiation. So that's 8 months. You go up to 10 years, obviously that's 15 or 20 times longer trip. And at that point, you're getting 15 to 20 times a lifetime's worth dose of radiation. And I think the math of that is that for the Mars trip, you increase the cancer probability, spontaneous cancer probability by mutations by about 10%. If you go into the outer solar system, I'm sure you're doubling or trebling it. So at that point, it's a really substantial risk you're taking. There's no way around it, though, because the energy costs of going to the outer solar system are so high that you can't put extra cladding or protection on the spacecraft. I mean, you can have the human encased in protective material in a spacesuit if you like, but that's the best you can do. So yes, these are very hazardous missions for people to undertake.
The next question is from Jennifer, who asks, what do you think about Avi Loeb's Galileo project? Are you familiar with it, and what are your thoughts on it?
I have heard of it, but I'm not locking in on what it is. I may have to come back on this one.
Okay, no problem. The next question is from David, who asks, how is it determined which exoplanets are safe from stellar flares ejecting from their host M-type stars?
Well, it's not known how they are protected. It depends, of course, on the thickness of their atmospheres. So the question's alluding to an issue that's arisen because we know that most exoplanets are going to be around dwarf stars, M-dwarfs, for example. These are cool stars that are maybe a quarter to a fifth of the mass of the sun. And these stars, even though they're dwarf stars, they actually tend to be quite active. They have very active chromospheres and coronas, and they accelerate X-rays. And so they're more X-ray active even than the sun relative to their size. And so this intense X-ray emission, variable X-ray emission, will be dosing a nearby planet. And remember that to be in the habitable zone of an M-dwarf, the planet is going to be pretty close to the star, closer than Mercury is to the sun, to be in a range for potential liquid water. But by being so close, it's also close to the X-rays. So there's a lot of debate amongst astrobiologists about whether planets around M-dwarfs are going to be habitable at all, because they're tidally locked for a start, and because they have such severe X-ray emission, mostly. And I don't think people have decided what the answer is. It may be that some planets with thick atmospheres can be sheltered from enough of this, and the atmosphere may even sort of buffer the temperature extremes that otherwise might exist between the facing and away sides of the planet, but really nobody knows.
The next question is another astrobiology question. Why did they recently take tardigrades onto the space station? What research do they want to perform on the tardigrades now? We know that they have amazing survival capacities, but what kind of research are they doing now?
Well, it was discovered accidentally. I mean, tardigrades have been known and studied for decades, and they have the amazing ability of cryptobiosis, which is to naturally reduce their water content to about 1% of normal and lower their metabolism by a similar factor of 100, essentially going into a wait state. It's an extraordinary capability. They also are very radiation resistant. And at least one instance of a tardigrade accidentally piggybacking on a Russian spacecraft has been recorded, and the tardigrade survived a week in a pure vacuum of space and cosmic ray and ultraviolet radiation exposure. On the space station, they just want to extend those experiments. They want to see how well tardigrades do in zero gravity, of course, which is, I doubt, a problem for a tardigrade, and also in a high radiation environment. They want to probably see how their metabolism works, whether they can still slow their metabolism or control it when they're in a different environment. So tardigrades are sort of model organisms as extremophiles for how species could adapt or live or survive in very challenging conditions. And so space station is a natural place to test these capabilities.
The next question is from one of our live participants who asks, is the Oort cloud even real?
We still only infer the Oort cloud. So I'm hesitating slightly because the Oort cloud has been part of astronomy for a long time, 50 or 60 years. Jan Oort was a famous Dutch astronomer who was an amazing character. He worked on all sorts of things. He worked in cosmology and galaxies in my field. He worked on planets, of course. He proposed the cloud of comets, the parent cloud of the comets that venture into the inner solar system, and he was working and active and writing papers into his 90s. Amazing man. The Oort cloud is the repository or the storage of the comets that visit the inner solar system. Remember, with a Keplerian orbit, and the highly elliptical one at that, comets will spend most of their times very far from the sun, moving very slowly in the deep freeze of space, at distances of tens of thousands of astronomical units. So that's so far away that the ability to directly see a 5 or 10 kilometer rock, cold rock, are beyond us. There's no way we can ever see comets in the Oort cloud. So we have to use the trajectories and properties of the subset of comets in the Oort cloud that venture into the solar system where we can measure them and see them to infer the properties of the whole population. So that's the inference that was done to lead to the Oort cloud. And there's nothing since the time that Oort first proposed it that's made it an implausible idea. So we think it's generally correct. The inference, of course, is amazing because the parent body, the parent Oort cloud, contains potentially 1 trillion comets. And almost all of them will never come into the inner solar system and be visible by us. So we're inferring this vast population at enormous distances based on a tiny fraction of the population that come close to us.
All right, the next question is from Richard. There's recently today a news story about the asteroid Bennu, which now has been found to have a higher than expected chance of hitting the Earth sometime in the next 300 years. The question from Richard is, Bennu is scheduled to hit Earth September 24th, 2182. Can it be avoided, or will we be able to divert it?
Yeah, I read that too, and it's not a firm prediction. We shouldn't take it that way either. There's also a close approach of Bennu in 2135 that they've been modeling. So they've been modeling episodic close approaches of Bennu, but a close approach is nothing like in the same category as a near impact or potential impact. The first thing you always remember is that space is enormous and Bennu is really small compared to the Earth. So the odds, even if it were coming somewhere near the Earth, that Bennu would impact the Earth are really tiny a priori going in. And the computer models of its trajectory are not accurate enough to say whether it's just going to come near or very, very near or dangerously near or actually hit us. But in all these calculations, the odds of it hitting us are the lowest probability. So I think that's a very distant prospect in time and also in the actuality of an impact.
The next question is from World of Science, who asks, how do objects in space become locked in their orbits, and how does resonance work on cosmic objects?
Well, the tidal locking, I presume, is what you're referring to. Tidal locking occurs when a moon, for example, is quite large compared to its parent planet and quite close to it. Obviously, we have objects orbiting other objects throughout the solar system. But when the relative size of the objects is not a large factor and the proximity is there, then the tidal force, that is the fact that the planet tugs on the moon larger on its near side than its far side, essentially aligns the moon in the direction of the planet, and that's tidal locking. That means that one face will always face the planet. That's what our moon has done, and various other moons in the solar system have done. Resonance is a slightly different phenomenon. That's the one where in an orbital situation, if you have a situation of two moons, any two moons of a planet, say, where their periods are the ratios of two whole numbers, that means that every sum number of orbits, some whole number of orbits, they will come close together, and so their gravities will interact, or they will interact by gravity fairly strongly. And because of the resonance situation, the whole ratio of whole numbers, that situation keeps coming up over and over again in a very repeatable and reliable way. And that can eventually lead to perturbation of the orbits or the ejection of one or more of the moons. So these resonance situations do naturally occur, and they can be long-term disruptive to the orbits of the objects involved.
The next question is from one of our live viewers who, Everything Psi, asks, does the influence of gravity extend out forever?
Yes, in principle it does. Gravity is an infinite range force, which means that in the Newtonian version, the force of gravity goes down as the square of the distance from the gravitational object. And although something goes down as the square of the distance means the force declines quite rapidly, double the distance, you get a quarter the force, triple the distance, 1/9 the force. 1 over the square of a very large number becomes very small but never zero, and therefore the force of gravity never goes completely to zero. It's an infinite force.
The next question is from Supreme Scientist, who sent an email. In our solar system, which planet is the oldest and which planet is the youngest, and how was that determined?
It's an interesting question, and it's not really one that's very easy for us to answer because we'd actually have to look at a model. So we do not have direct measurement of the age of all the planets in the solar system to answer the question experimentally. We only have measured, based on radioactive decay, the direct age of the Earth and the Moon. And the Earth is very slightly older than the Moon, so we know that difference. It's a few tens of millions of years on an age of 4.52 billion years. We haven't measured, we do have Mars rocks, and so we know the Mars is about the same age as the Earth. It's not a very precise measurement. And we have no samples to work with for the other planets to measure their ages. So without direct measurement of ages, we're left with the model of the solar system's formation and consistency checks on that. And all these models currently suggest that the entire solar system, which is to say the rocky cores of all planets, formed within a very short time after the formation, 5 to 10, maybe 15 million years. And within that, if you believe the model, there maybe is an inside-out mechanism working, where you would believe the inner planets, the rocky terrestrial planets, formed slightly earlier than the outer gas giant planets, their rocky cores forming first, and then the gaseous mantles being drawn onto them. So those fully fledged giant planets took a little longer to form. But that's, again, a model. We don't have direct measurement.
The next question is from, I'm not sure how to pronounce the name, but Candy Rotter, who asks, could we at any time watch or see the shape of the Milky Way galaxy, or are the images that we see on the internet just an estimation of the shape that it could be?
Right, we're stuck in the galaxy. We're in the disk of the galaxy, and so we can't rise above it and see what it looked like from above. When you see suggestions of that, they're based on the shape of other galaxies, where we are looking down on the spiral pinwheel, and we think they're similar. So it's a little indirect to talk about how the galaxy would look from above. However, even though we're buried in the galaxy, in the disk, we can see the shape of the galaxy because when you use radio waves, light does not travel through the galaxy. The center of our galaxy is hidden from us completely. Only 1 in a trillion photons reaches us from the center of our galaxy. It's like looking through a closed door. However, radio waves travel freely through the gas of the interstellar medium, and so we've used radio measurements to map out the galaxy and especially its rotation all the way through to the center and out to the edges. And that allows us to reconstruct the way the galaxy moves and indirectly the way it looks, even though we can't see it from above.
All right, so we have about 5 minutes left for, oops, sorry, I didn't turn the microphone up. So we have about 5 minutes left for our live session. Thank you all for joining us. So we probably have time for about 2 questions, possibly 3. I wanted to mention quickly that going forward, we have a Google Calendar that we set up that will let everybody know when the live sessions are coming up. If you got an email from our course management system from Coursera or Udemy, if you're in our classes, the link is in that email. And if not, then we'll post it on our Discord server, and I'll post it in the chat so that you can link up or subscribe to our Google Calendar, which will tell you all of the upcoming live sessions. And so you can set that up on your calendar. That will be another way if you have fallen off of an email list or are not on one of our regular email lists. This is another way to get those notifications. All right, so the next question is from Mayful, who asks, could you please explain Cherenkovs radiation?
Yes, Cherenkov was a Russian physicist from the early 20th century. Cherenkov radiation is the radiation that happens when a particle, charged subatomic particle, is moving very close to light speed, and especially on a curved trajectory. It releases a shell of radiation, a flash of light, if you like, so the particles are moving relativistically, and that's a sign that we have a charged particle moving very rapidly. And so astronomers have learned how to use Cherenkov radiation to detect charged particles, even though they don't detect the particle itself. They can detect the flash of radiation, the Cherenkov radiation that the particle produces. And so there are Cherenkov detectors that have been used in high-energy physics and in astrophysics to look at high-energy phenomenon for decades. It's a very mature technique of astronomy.
Excellent. The next question is from one of our live participants who asks, pardon me, sorry, I lost where it was. AB asks, why is it that we can see stars that are billions of light years away, but we have such a hard time seeing planets a few light years away very sharply?
Because planets are small and they don't emit their own light. So we can see stars at great distances. We can't actually see individual stars at enormous distances. Probably the largest distances we can see individual stars in nearby galaxies with things like the Hubble Space Telescope is maybe 30 or 50 million light years. That's a small fraction of the distance across the universe, but it's obviously very far away. And we can see them because stars, especially luminous stars, red giants or supergiants say, are extremely luminous, many photons per second. Planets don't emit any of their own light. So at a minimum, a Jupiter-like planet around a Sun-like star is only reflecting about 1 in 100 million photons. So it's 100 million times fainter than the star it orbits. And an Earth-like planet is 1 billion times fainter than the star, a Sun-like star that it orbits. So these incredible reductions in brightness because of the planet not emitting its own light is what makes imaging or seeing planets directly so hard. And the second thing, of course, is that as seen from afar, solar systems are quite small. And so the planet will also be seen to be orbiting the star very close on the sky, fractions of an arcsecond. And that makes it even harder to see this very dim reflected light when it's so close to the star itself.
All right, we have time for one final question. This one is from Kenny Smith, who asks, are there any stars outside of galaxies? How do you detect them, and why does that happen?
Yes. there are stars outside of galaxies, and it was a surprise. Some theorists predicted this, but it's been known for a few decades, and there's been a lot more work on it in the last 10 years. There are stars outside of galaxies, which is to say stars that are not bound to the galaxy, whereas the Milky Way has a lot of stars that are in highly elliptical orbits in the halo, and a lot of stars in the disk, like us, the Sun, which are in circular orbits in the disk. There are a very small number of stars that have velocities that say they must have escaped. So any star with a velocity, radial velocity of more than about 300 kilometers per second is not bound to the Milky Way, because that's the highest rotation or orbital speed we see in the Milky Way. And there have been dozens, maybe a few hundred of these stars found, and they're called hypervelocity stars. The question of why they can do that or how they do that was interesting to solve. It was a theoretical puzzle in part. And it now turns out that these are almost all stars that originated in binary or triple systems. So if you have a violent interaction of stars in a binary or triple system, possibly because the system is collapsing and the stars are about to merge, then it's possible for one of the members of the system, one of the members of a binary pair, or actually even better, one member of a triple system, to get an enormous kick, to get an extra velocity. It's not getting energy from nowhere, it's getting energy from the other stars in its little tight system. And that energy is sufficient to liberate it from the galaxy. And since this has been happening for a long time, since the Milky Way started, then presumably intergalactic space, the huge voids between galaxies, are filled, well, not filled because there's so few of them, but they have a smattering of intergalactic stars that are just whizzing through space. Some of these kick velocities can be 10-20% of the speed of light. So it's an extraordinary scenario to have individual stars ejected from their galaxies flying through intergalactic space at significant fractions of the speed of light. And just the final wrinkle on this, if those stars happen to have planets on them, around them, those stars would not necessarily be disrupting. As they got ejected, they could retain their planets in their orbits, especially if they're on tight bound orbits. So you could also have Earth-like planets flying through intergalactic space attached to stars that have been kicked out of the center of their galaxy, and possibly life on those planets as well, where the universe would look quite different than it does from here on Earth. Okay, that was a nice question to finish with, a speculative one, but real science, and good questions today, as always. We'll be back with you in a couple of weeks. Thanks to Matthew for facilitating. I think this calendar tool will be helpful for people planning future sessions. Okay, thank you.
Excellent. Thank you, everybody. Have a great rest of your day or evening or morning, depending on where you are. Take care.